It was 10:26 p.m. in Moscow at the moment of ignition. The rocket was 1,500 miles to the east, its very existence a closely guarded state secret. On the other side of the Iron Curtain, that afternoon proceeded as usual. It was a fairly quiet night. Not until late into the evening in the West was it announced via Moscow radio that an achievement was made that would change the course of history forever. It was nothing more than a 2-foot-wide metal sphere, sprouting 4 antennas and transmitting a 1-watt signal in the 20 and 40 megahertz range, putting it within the audible scope of nearly any radio amateur. Perhaps no other recorded sound in history has had a greater effect on the psyche of the American people. It was October 4th, 1957. They called it Sputnik. Literally translated, it means satellite, but perhaps more aptly, it meant companion. For this was the first time that an artificial object was placed in orbit of the Earth. What had existed merely as a remote and improbable concept on paper for nearly 50 years had been realized, from the perspective of scientists in the United States, almost overnight, chaotically shifting the perceived balance of technology, power, and influence irrefutably in favor of the Soviet Union. The space race had begun. The resulting pressure on the Eisenhower administration to bridge this so-called missile gap led to perhaps one of the greatest centralizations ever witnessed in American government. With the stroke of a pen, dozens of isolated and independent aeronautical research institutions now took their marching orders from a brand new bureaucracy, the National Aeronautics and Space Administration, established July 29, 1958. It would be clear for some time that the Russian space program would stay ahead. With their advanced propulsion systems and operational experience, the Soviet Union continued to rack up an impressive series of manned and unmanned firsts. As the Soviet Union continued to gain early achievements, the U.S. government continued to move the goalposts and raise the stakes, culminating in a declaration of the intent to land a man on the moon by 1970. Throughout the 1960s, as NASA's manned space program continued to gain steam, draw crowds, and produce political capital, unmanned exploration still continued. The Jet Propulsion Laboratory, now within the NASA umbrella, was primarily responsible for the design and operation of all unmanned exploration spacecraft. The Ranger Lunar Impactor Series, the Lunar Orbiter Series, and finally, the Surveyor Lunar Landers. It was decided in May of 1960 that the unmanned program can and should reach for much greater distances than had ever been before imagined. These new missions, called Mariner, would see upgraded Atlas rockets with new upper stages, boosting ultralight electronic explorers to unbelievable speeds. Speeds that may just be enough to facilitate travel between the planets. Man's physical exploration of the solar system was about to begin. Spearheaded by the Chief of Advanced Technology Programs, Edgar Cortright, Mariner's objective as an overall program was to use light and medium-lift launch vehicles to place scientifically oriented robotic probes on missions towards the planets. Like many of NASA's early unmanned efforts, the first Mariner mission was a disaster. 5 minutes after launch, Mariner 1 was remotely destroyed when its Agena upper stage started veering off course. But on August 27, 1962, as NASA's Mercury astronauts were making America's first manned orbital flights, Mariner 2 became the first spacecraft to successfully fly by Venus, securing an important first for the United States. Mariners 3 and 4, also identical missions, were both launched towards Mars. Although Mariner 3 failed, Mariner 4 was a success. Mariner 5 finally broke the streak when it successfully flew by Venus in 1967. NASA's second visit to the planet, it carried out more detailed scientific analysis of its upper atmosphere. Mariners 6 and 7, again identical twin missions, were both launched towards Mars. They performed close flybys and provided NASA with the first ever up-close and detailed images of the Red Planet. Slowly but surely, the Mariner program trudged on, living in the shadow of Apollo. As astronauts continued to bounce around on the lunar surface, robotic explorers continued to photograph nearby planets. Mariners 8 and 9, the final twin missions, were also launched towards Mars. Unlike prior flights, however, they were going to decelerate and enter Martian orbit. Mariner 8 was lost in a launch vehicle failure, but Mariner 9 successfully became the first spacecraft to orbit another planet, narrowly beating the Soviet attempt by less than a month. The Soviet Union, however, would be the first nation to successfully soft land on Mars. Their lander failed within 20 seconds of operation, attributed to the dust storms then occurring at the landing site. After 13 long years, the Mariner program had run its course. It was now 1973, and the days of unlimited budgets and endless political support for the space program were over. The first 9 Mariner launches, spread out over a decade, included 3 intended for Venus and 6 for Mars. Their success is what now enables a bold finale, one that will serve as the capstone to a program that had forged a legacy of success. The 10th and final Mariner mission, scheduled for a November 1973 launch, is the first ever flight that will attempt to perform a gravity assist. Mariner 10's planned trajectory will take it on a flyby past Venus, using its gravity well to further bend the outbound trajectory towards Mercury. This maneuver, inspired by the Italian mathematician Giuseppe Colombo, will allow Mariner 10 to continue operating in trans-Mercurian space, enabling multiple flybys of the first planet. Mercury is located deep within the gravity well of our parent star, and is an infamously difficult planet to reach. Only by using Venus's gravity as an orbital slingshot is it possible to reach Mercury with enough operating fuel to perform basic attitude maneuvers and allow for the gathering of scientific data. Cost effectiveness and fuel efficiency are the top priorities of the Mariner 10 mission, which must not exceed its strict $98 million allocated budget. This is the first time in NASA's history that the agency subjected a mission to an inflexible budget constraint. Mission planners are forced to carefully consider cost efficiency at every stage in the flight. As a result, several unorthodox methods of flight control and launch preparations are carried out. Mariner 10, which will be electrically powered by solar panels, will utilize partially extended panel configurations to exploit solar radiation pressure as a means of attitude control to conserve fuel. In other words, the solar wind generated from our star will be harnessed by the physical shape of the spacecraft as an effective sail, allowing it to adjust its direction without using fuel. Cost control was accomplished by executing contract work closer to the launch date than previous missions. Reducing the length of available work time increased cost efficiency. Corners were cut, but despite the rushed schedule, very few deadlines were missed. The mission would ultimately end up $1 million under budget. The Mariner 10 spacecraft was built by Boeing and housed what were at the time intricate and complex electronics. Over 32,000 pieces of circuitry, including resistors, capacitors, diodes, microcircuits, and transistors. Commands for the various scientific instruments and attitude control system were stored on Mariner 10's computer. This computer was limited to only 512 22-bit words. All other programming had to be broadcast from the Earth. by the Mission Sequence Working Group. The solar panels that supply the spacecraft's electrical power are connected to a booster regulator and an inverter, converting the panel's DC output to AC and altering the voltage to the necessary level. The onboard battery can store 20 amp-hours of electricity on a 39-volt nickel-cadmium cell. This would be the first time a spacecraft had ever operated at such close proximities to the Sun, and the resultant heat and solar radiation that would be encountered had to be kept in check by innovative new precautions. Spacecraft parts would need extra shielding. Mission planners chose beta cloth, the same material used in Apollo spacesuits, for thermal blankets to be placed on spacecraft components. The two solar panels themselves needed to be kept under 240 degrees. Covering the panels would defeat their purpose of producing electricity, so the solution was to place them on a rotating servo. They could be tilted, and the angle at which they faced the Sun could be changed, much like how the lunar surface is heated to a lesser degree during periods of low sun angle. For the spacecraft body, there is even a small deployable sunshade. Mariner 10's small maneuvering engine, fueled with hydrazine, had to be kept warm to prevent its fuel from freezing. Thus, it was to face towards the Sun during coast periods. A special paint was applied to exposed parts on the rocket so as to reduce heat flow from the nozzle to delicate instruments on the spacecraft, which were located mere inches away. The engine and fuel system on board the probe is capable of imparting a total delta V of just 266 miles per hour, or 119 meters per second. The cold gas RCS system was powered by nitrogen. If Mariner 10 was to successfully maintain a course towards Mercury, it would have to pass no further than 120 miles from a precise, critical point in the vicinity of Venus. The accuracy demanded from this flight, compounded by the utter lack of extra fuel, would place an extreme burden on the navigation and targeting capabilities. JPL had to get it right. There were no second chances. Of 46 submissions, only 7 scientific instruments are chosen to fly aboard Mariner 10. The heaviest of these would be the cameras. The imaging system consists of 2 15-centimeter Cassegrain telescopes feeding Vidicon tubes. Each telescope has an 8-position filter wheel. The cameras weighed 96 pounds. The other scientific experiments include plasma science via a scanning electrostatic analyzer and an electron spectrometer for measuring the solar wind and planetary radiation belts. 2 triaxial flux gate magnetometers for mapping the magnetic fields of Venus and Mercury. An infrared radiometer for temperature measurements and thermal imaging. Extreme ultraviolet air glow spectrometers for analysis of upper atmosphere luminosity, and even the observation of a deep space comet during the transit. A charged particle telescope will survey high-energy particles in space by direction, kind, and intensity. Finally, celestial mechanics and radio science will be conducted by an X-band transmitter that can also be used to communicate with the Earth as a backup to the primary communications antenna, which transmits in the S-band frequency. Both frequencies exist within the microwave radio region of the electromagnetic spectrum. In total, the space probe weighs just over 1,000 pounds, of which only 64 pounds is fuel. On November 3rd, 1973, the Atlas Centaur rocket roars to life. The perilous journey of Mariner 10 has begun. Mariner 10 spends only 25 minutes in the parking orbit. The Centaur upper stage fires up again and shoots Mariner 10 into an outbound hyperbolic trajectory away from the Earth at nearly 28,000 miles per hour. Only a few hours later, planet viewing experiments were turned on. The aim was to calibrate the instruments in the well-known environment of the Earth-Moon system, thereby effectively providing a 4-planet space mission and giving scientists on the ground an early indication of the spacecraft's health. The Scanning Electrostatic Analyzer, one of 2 instruments that comprised the plasma detection experiment, was stuck behind a protective door that jammed closed. An unsuccessful attempt was made to forcibly unfasten the door with a course correction maneuver. JPL had hoped to observe the behavior of positive ions and electrons with this instrument. Unfortunately, for the rest of the mission, it would remain in this crippled state. The other plasma detector, and indeed all other scientific instruments on Mariner 10, appeared to be in excellent health. The near-Earth calibration gave mission personnel confidence in the performance of the spacecraft and her instruments. Everything was set. Mariner 10 had begun the Trans-Venusian coast phase. As fate would have it, another problem developed. 2 heaters surrounding the aluminum telescope barrels of the TV cameras failed to turn on as scheduled despite repeated commands. If temperatures dropped too far, the optics and other mechanical parts could sustain damage. It was decided not to shut the Vidicon tubes off, leave them on, and hope that whatever tiny amount of heat generated would be enough to keep them within working limits. Fortunately, the temperature eventually stabilized. So far, so good. Much later in the flight, the heaters would suddenly begin working. The exact cause for their initial failure remains unknown, but likely the result of a short circuit. As she coasts silently on towards Venus, Mariner 10 executes several roll calibration maneuvers. The ultraviolet spectrometer scans the celestial sphere, providing data on the spatial distribution of neutral hydrogen and helium emissions. Data from Mariner 10 is downloaded at a rate of 2,500 bits per second, thanks to the addition of 2 210-foot radio antennas recently added to the Deep Space Network at Madrid, Spain, and Canberra, Australia. On the way to Venus, 2 course correction maneuvers were made. The first one is 17 miles per hour, or 7.8 meters per second, and it eliminated minor errors in the initial injection. A second maneuver took place on the 21st of January 1973, shifting the aim point to within 8 miles of the critical target. Mariner 10 was precisely on track. In late January, observations are made of the comet Kohoutek with the ultraviolet spectrometer. These observations are unique to ones made on Earth or even in low Earth orbit. Earth's geocorona tends to block out some of the weaker signals of neutral hydrogen emissions. C-1973 E1 Kohoutek was first observed by mankind the very year Mariner 10 was launched, in March of 1973, by Czech astronomer Lubos Kohoutek. Kohoutek's origins are deep within the Kuiper belt. Mathematical calculations on its orbit indicated that the last time it had passed through the inner solar system was 150,000 years ago. Due to gravitational perturbations from the outer planets, Kohoutek had been accelerated and is widely believed to have temporarily achieved escape velocity. Later calculations, however, indicated that Kohoutek may have been slowed by Mars on the outbound trip, and that it will return again to the inner solar system, some 75,000 years from now. In other words, Comet Kohoutek had been the subject of a coincidental gravity assist, setting an example for the mission of Mariner 10 to strive for. On January 28th, Mariner 10 performs another routine roll calibration maneuver. This time, however, heavy oscillations are observed in the roll axis. The onboard computer attempts to null these out, but only makes them worse. In the time it takes JPL to recognize, analyze, and respond to the problem, some 16% of the total attitude control gas was uselessly expended. The problem resulted from the solar panels. They were wobbling, induced by impulses from the gas jets mounted on their ends. Following extensive troubleshooting, the movable components of the solar panels were rotated in such a way as to avoid further oscillation, allowing Mariner 10 to conduct future maneuvers under certain conditions. Further roll calibration maneuvers were canceled. Finally, Mariner 10 approaches the second planet from the Sun. February 5th, 1974. Arrival at Venus. With a diameter 95% of Earth's, nearly identical density, and overall similar chemical makeup, Venus is often referred to as Earth's sister planet. In qualitative terms, however, this could not be less accurate. Its surface is obscured by a thick, sulfuric atmosphere. Venus appears, from space, as a sort of terrestrial pearl, its soft, pastel-like appearance giving no indication of the hellish conditions below. Venus takes 224.7 Earth days to orbit the Sun, and makes one complete rotation on its axis every 243 Earth days, meaning that a single Venusian day lasts longer than a Venusian year. A solar day lasts 117 Earth days. Venus's atmosphere is 96% carbon dioxide, but the most visible part lies within the remaining 4%, which includes its opaque upper atmosphere of highly reflective sulfuric acid clouds. The remainder is free nitrogen gas and a smattering of other trace elements. The atmosphere is 93 times thicker than that of Earth's. The pressure on the surface of Venus is equivalent to being 3,000 feet underwater. This doesn't stop high-energy radar waves from pinging its surface and providing humanity with a unique look at the land below. Thanks to its greenhouse atmosphere, Venus is by far the hottest planet in the solar system, even hotter than Mercury. The average surface temperature is 863 degrees Fahrenheit, 462 Celsius. While a weak Hadley-type atmospheric circulation does exist at the subsolar point, Venus is effectively isothermal. Temperatures do not vary between daytime and nighttime. Its surface is a vast, endless desert, dotted by dormant volcanoes and angular boulders. There doesn't seem to be any evidence here of plate tectonics. As a result, the topography of Venus is fairly tame, save for a handful of massive volcanoes likely originating at geologic hotspots. 80% of the planet is comprised of a smooth, volcanic plain. The tallest mountain, Maxwell Montes, is 7 miles high. The geologic age of Venus's surface is fairly young at 600 million years, though much older than Earth's. Earth's crust is continually recycled via subduction at the boundaries of tectonic plates. Venus has no tectonic plates. It is, however, geologically alive. It is suspected that every few hundred million years, consistently rising temperatures inside of Venus's mantle reach a critical point that fundamentally weakens the outer crust. Then, over a period of just 100 million years, a global resurfacing event takes place in the form of an apocalyptic series of massive volcanic eruptions, releasing eons worth of pent-up energy in a single era. Scientists currently believe we may be on the cusp of the next such event on Venus. Without seismic data from the surface of Venus, little information is known about its internal structure. Over 160 volcanoes on Venus are well over 100 kilometers or 62 miles across. The planet has several times as many volcanoes as the Earth. Given the harsh surface conditions, it's practically impossible for any spacecraft, manned or otherwise, to survive here for any meaningful period of time. But that hasn't stopped nations from trying. In the years immediately preceding and following the mission of Mariner 10, the Soviet Union's Venera program would see no fewer than 8 successful soft landings on Venus. The massively robust but primitive landers transmitted little in the way of useful scientific data. Several Venera landings in a row even had faulty lens caps that didn't deploy from their cameras, and in one case, a lens cap landed directly under the surface sampler. However, a few precious images from the surface of Venus do exist. No probe lasted longer than 2 hours before dying and inevitably melting. Another shocking discovery is the fact that Venus's magnetic field is incredibly weak, indicating the planet may only have a small amount of iron in its core. Venus's magnetic field is less than 1/20th of 1% of Earth's, and is insufficient to deflect the solar wind. As a result, the outermost layer of the atmosphere, the ionosphere, is steadily stripped away by the constant stream of high-energy solar particles, forming a faint but detectable tail, similar in many respects to that of a comet. The faint magnetic field that does exist around Venus is thought to be generated by the interaction between the ionosphere and the solar wind, rather than the internal, core-powered dynamo effect that enables conventional magnetic fields, such as Earth's. Without any solid data from Venus's interior, there are many possibilities as to why this could be the case. It's possible that there is a total lack of convection in Venus's outer core. Another possibility is that Venus has no solid inner core. Yet another is that its inner core may have already entirely frozen. The dynamo-based magnetic fields, like that of Earth, rely on a massive amount of heat flux between a solidified, rotating inner core and a molten outer core capable of liquid convection. For some reason, these processes seem to have stopped altogether on Venus. Even still, there was something intriguing about the current state of Venus. 4.5 billion years ago, when the solar system was just beginning to form, it is known that the Earth could not have condensed from the protoplanetary disk with the current amount of water it has today, indicating that a large majority of Earth's water and other volatiles were delivered to the surface after our planet had already formed. When and how that water was brought to Earth is the subject of ongoing research. One unique window into that period of time is the Moon. With a surface largely unchanged since its formation, Earth's moon is essentially the fossil record of the inner solar system. And the Moon has quite a story to tell. The petrology record on the Moon suggests a cataclysmic spike in the cratering rate just 700 million years after the formation of the planets. Planetary formation theories cannot naturally account for such an intense, concentrated period of planetesimal bombardment. The leading theory suggests a rapid migration of the outer planets, Jupiter, Saturn, Uranus, and Neptune. We like to think of planetary orbits as being static, stable over incredibly long periods of time. However, the current orbital spacing between the outer planets suggests that at one point Jupiter and Saturn were much closer together and shared a 1:2 mean motion resonance. In other words, for every 2 orbits of Jupiter, there would be 1 orbit of Saturn. This implied a regular series of intervals in which Jupiter and Saturn would share an uncomfortable proximity. Thanks to subtle interferences of their orbits from smaller bodies, at some point, the 2 gas giants were close enough together to affect their orbits. Saturn was flung further out into the solar system by the much more massive Jupiter, causing dozens of moons to collide and possibly forming the massive ring system it has today. Now orbiting through new space, the presence of Saturn wreaked havoc on the outer solar system. A Saturnian flyby of Neptune caused that planet to be ejected on an orbit that took it further from the Sun than Uranus, which had initially been the outermost planet. Neptune then travels into the Kuiper Belt, grabbing millions of tiny asteroids, each filled with a rich mixture of water, methane, and ammonia ice, and then throws them into the inner solar system, where they then bombard the inner planets, Mercury, Venus, Earth, and Mars, delivering untold quantities of water to their surfaces. In the case of Earth, a ballpark figure is 1,450 quadrillion tons of water. This event, in the context of Earth's natural history, immediately precedes the first signs of life. The end of the late heavy bombardment and the beginning of life on Earth are so close together that it's possible that life itself was delivered here as a result of this solar system revolution. In the context of Venus, however, assuming the process that delivered water to Earth was common to all the planets near the habitable zone, it is estimated that liquid water at one point existed on Venus's surface, and possibly could have stayed there for 600 million years, during and shortly after the LHB. Much like Mars, Venus at one point hosted vast shallow oceans on its surface, perhaps teeming with microbial life. We aren't entirely sure why, but for some reason, Venus suffered from a runaway greenhouse effect. Perhaps a symptom of its lack of a powerful magnetic field. Perhaps caused by an orbital migration that brought it closer to the Sun than it had formed. Either way, the surface temperatures on Venus continued to rise, and the greenhouse gases in its atmosphere enabled a positive feedback loop that eventually boiled all of its oceans away, leaving it in the state it exists today, with a surface temperature higher than that used for sterilization. Thanks to the periodic global resurfacing events, we don't know how long water existed on Venus. We do know, however, that liquid water existed on Mars for at least 1 billion years. If that's any indication, then Venus could have, at one time, been the hot, humid jungle that early humanity believed it to be.
The results of the Mariner 10 photography in the ultraviolet were really good. In fact, much, much better than we had hoped. Because, as you can see, looking at first a picture of Venus in the visible that was taken by Mariner 10, and then when we switched to one that was taken in the ultraviolet and has been enhanced with a computer to bring out the details, there's a tremendous pattern of organization of markings. Let's take a look at what's in these pictures. The most prominent thing that one can see is a very bright south polar cap, probably a great vortex, almost like a huge cyclone. And there are dark streaks that come into this as though they're winding up like taffy. So the whole series of mosaics was like a series of snapshots of Venus in time. And from those mosaics, it was possible to create a time-lapse movie of the rotation of the Venus atmosphere during the period of time Mariner 10 flew by and flew away from the planet. the pattern of rotation of features on Venus in the upper atmosphere, way up high by our standards, is remarkable in that the atmosphere on Venus rotates faster than the surface. In the case of the Earth, the atmosphere tends to drag behind a little bit, as one might imagine. In the case of Venus, the atmosphere rotates all the way around the planet once every 4 days. The surface rotates once every 243 days. So the atmosphere is rotating almost 60 times as fast, at the top anyway, as the planet itself.
A third course correction places Mariner 10 on a trajectory that would take it just 625 miles off the surface of Mercury on the 29th of March, 1974. Mariner 10, being the first spacecraft to ever visit Mercury, reveals its surface as never before seen by humanity. The smallest planet in the solar system is, by appearance, remarkably similar to our moon, indicating that it has been geologically inactive for billions of years. Mercury's orbit is the most eccentric of any planet. Its perihelion is 33% closer to the Sun than its aphelion. Having no atmosphere to retain heat, the surface temperature ranges from 800 degrees during the day to negative 250 degrees during the night, 427 to negative 93 Celsius. The polar regions are consistently below freezing. Physically, Mercury is smaller than some of the larger moons in our solar system, such as Ganymede and Titan. It is, however, one of the densest. Second only to Earth, Mercury appears to have an extreme amount of iron in its core, which makes up for some 55% of its volume. Earth's high density is a result of gravitational compression. Mercury is much smaller, and its inner regions are not as compressed. Therefore, such a high density can only be explained by a core that's large and rich in iron. Such a large amount of iron is only possible if Mercury was struck by another planet early in its formation, combining the two cores and stripping away a large amount of the mantle and crust, which subsequently fell into the Sun or struck other inner planets. Alternatively, Mercury could have been formed from the solar nebula before the Sun's energy output had stabilized, and was much bigger than it is today. As the proto-Sun contracted, temperatures near Mercury could have been as high as 10,000 Kelvin, nearly 18,000 degrees Fahrenheit. Much of Mercury's then surface rock would have been vaporized by such temperatures, forming an atmosphere of rock vapor that was carried away by the solar wind. Despite being only 75% as large, Mercury's surface gravity is essentially the same as that of Mars. Unlike the Moon, there are large scarps on Mercury, cliffs nearly 2 miles high and stretching intermittently across its surface. The largest basin, Caloris, features an unusual pattern of cracks on its floor. Mercury makes one complete orbit every 88.97 days. Like Venus, it takes longer to make a complete rotation. A solar day on Mercury is equivalent to 2 Mercurian years, just under 178 days. Relative to the stars, it rotates on its axis exactly 3 times for every 2 revolutions it makes around the Sun. This is a form of being tidally locked, known as a 3-to-2 spin-orbit resonance. As our spacecraft traversed near Mercury, the Charged Particle Experiment observed an amazing series of electron and proton bursts, many orders of magnitude above interplanetary levels. This unexpected find was associated with the observation of a planet-related magnetic field, suggesting that part of Mercury's core is still molten. Mercury's magnetic field is 20 times stronger than Venus's. This is significant enough to deflect the solar wind. An aurora is the impressive end result of a series of events that starts with the solar wind. When these particles reach a planet such as Earth, they compress the magnetic field into the shape of a teardrop. Some particles are accelerated by this field into the upper atmosphere, where they collide with gaseous molecules such as nitrogen and oxygen, giving off energy in the form of light. Mercury practically has no atmosphere, but trace gases do exist. While there is no visual evidence for aurorae at Mercury, it is possible in some circumstances that trapped pockets of gas would be ionized by the solar wind. Further investigation is required. Mariner 10 makes 2 more flybys of Mercury throughout late 1974 and early 1975. By the last flyby, occurring on the 16th of March 1975, the flight hardware was beginning to show signs of aging. The failure of a tape recorder, the loss of more precious fuel after various attempts by the star tracker to lock onto Canopus, and the total failure of roll control were the first indications that the mission of Mariner 10 was coming to an end. A mission that had brought over 7,000 images of 2 very unique planets in our solar system, and provided priceless data on their current physical nature and insights into their past. After a series of engineering tests, the spacecraft began drifting uncontrolled on March 24, 1975, signaling that it had exhausted its onboard maneuvering propellant. Shortly thereafter, the command was given from Earth to shut down. The mission of Mariner 10 would provide the groundwork for future missions to follow. Building off of its legacy, later unmanned missions to Venus, such as Magellan or Japan's Akatsuki, taught us even more about the extreme world. Mercury would remain unvisited for 33 years, until 2008, when NASA's Messenger probe, using the same techniques of gravity assist that Mariner 10 had pioneered, was able to not only visit the tiny world, but even enter orbit and provide more than 4 years' worth of continuous scientific observation. Thanks to these flights, made possible by Mariner 10, we know more now about the inner solar system than we ever could have hoped for in 1973. Mariner 10 is still out there, orbiting the Sun in trans-Mercurian space. A silent relic from a classic era, slowly drifting, but never forgotten.